How's that? All right, recording is rolling. It's Friday, December 13th. That was fun. I got some pictures. Right. Oh, yeah, I did return you guys' energy momentum quiz. It's back in your folders. So if you guys want to get it at some point, you guys can do corrections just like all the quizzes we've done so far this semester. If it's a conceptual question, just write out the sentence. If you have to solve it with an equation to get a numerical answer, then you have to set up the equation and solve it. Right, for like that. All right, so I'm trying to continue the midterm review. Got my computer ready to go. Okay. Gemini meteor shower tonight. So if you guys watching the sky tonight, might see some shooting stars. Here's some upcoming rocket launches. All right. Let's do. All right, give you guys a minute to hop on Kahoot right there. All right, here we go. When car speed triples, its kinetic energy. Increases 9 times. Right? So 1/2 mv squared. Right? If you square the v, it'd be 9 times. Yeah, so 3 squared is 9. Yeah. All right, got points on board. All simple machines ideally work on the principle that I got force equals mass times acceleration. We got work input equals work output. Total momentum before collision equals momentum after a collision. Kinetic energy transforms to potential energy. Now, each of those statements could be true in isolation, but which one applies to simple machines? Right. Oh, there you go. Work input equals work output. I have in front of me a pulley system right here. So do you guys see a small input force could lift a very large output force, right? But the catch is I have to pull lots and lots of string on this side, and the output force, well, it only moves up a little bit at a time. If I multiply force times distance input and force times distance output, at best these could be equal to each other. Yeah, so it's like a conservation of energy principle. Here we go. All right, we got Luke, Tristan, Sloan, Sophia. How many joules of work are done on a box? Force 25 newtons, push 3 meters. Yeah, 75 joules. Right, so as long as the force is constant, you can just do force times distance. Right. Now, give you guys a little twist on this one. Do you guys remember? I think on your last quiz, did you guys have a Hooke's law question with like compressing a spring? Right. Yeah. Now that was a variable force because you guys know Hooke's law. The more you press the spring, the more force it takes to press it even more. Right. So the area under that curve looks more like a triangle shape. Right. So you have to treat it like a triangle. Versus this Kahoot question, if the force is constant, you just do force times distance. Right. All right. Go. Got Luke, Tristan, Sloan, Sophia. How much power to do 40 joules of work in 5 seconds? Yeah, 8 watts. Okay, 40 joules in 5 seconds. 40 divided by 5. That'll be 8 joules per second, 8 watts. There you go. So power is a rate of energy transfer, rate of work. All right. Luke, Tristan, Sophia, Sloan. Where does a satellite in elliptical orbit have greatest kinetic energy? I look for closest to the planet. So if it's elliptical orbit, at some point it'll be closest to planet, at some point it'll be furthest away. So the distance changes. You know, if the distance from the planet is changing, the potential energy is changing and the kinetic energy is changing. Okay. So when the satellite's really close to the planet, is potential energy large or small? Well, if it's close, that'd be like a small height. So there'd be a small potential energy, which would therefore be a large kinetic energy, right? Right? Small potential, large kinetic, right? And then the large kinetic would be like the fastest speed. That's what it would be. Yeah, it does. So when it's close, it's gonna speed it go faster. And when it's far away, it's going to slower. Yeah. So like for example, here, maybe I can draw this out for you guys. Here, draw it here. Right. Oh, an example of something that has a highly elliptical orbit would be a comet. Right. So like planets going around the sun, yeah, it's elliptical orbit, but it's kind of close to circular. But comets have these highly elliptical orbits. So this might be the orbit of a comet. Right. When the comet's here, the kinetic energy is large and the potential energy is small. Right. So it's going to zip by really fast. Zoom. Okay. When the comet's way over here on the other side, it has a little bit of kinetic energy and a lot of potential energy. So it goes kind of slow. And so zoom, something like that. Okay. There you go. All right. What remains constant for a satellite in elliptical orbit? Constant is the total energy. Yeah, if you add together kinetic plus potential, yeah, the total energy is constant. Well, that'd be conservation of energy. Right? Conservation of energy. I got Luke, Tristan, Sloan, Sophia. Whoa. Machine puts out 100 watts of power for every 1,000 watts input. What's the efficiency? Hey, 10%. There you go, 10%. Right. So it's sort of an example that's not too different from this. When you guys drive your car is burning the gasoline to make the car go. Right. If you look at the total energy in that gallon of gasoline and the total energy that makes the car go, your car is somewhere between about 20 to 30% efficient. Right. Do you guys drive your car around and then say put it in park and you feel the engine and the engine's really hot? Right. Well, that's a lot of waste heat that was diverted. That didn't make the car move, but that would be some like inefficiency, right? Yeah. So only about 20 to 30% actually makes the car go. All right. Potential energy. Energy an object has because of its. Yeah. So I know the formula goes mgh, right? Mass times gravity field times height. So if I see any of those, right, the only option is like height, right? So mgh, right? Ooh, guys, what's the type of energy related to speed? That'd be kinetic, right? All right. I got Luke, Sloan, Tristan, Sophia. Table tennis ball launcher is fired. Compared to the force on the ball, the force on the launcher is. Yeah, same force, right? Ooh, hey, which law of motion is that? Newton's third law. Newton's third law. Equal and opposite forces. Equal and opposite force. All right, so when the ball is inside the barrel of the launcher, there's just some explosion that pushes equally in all directions. Yeah, so equal and opposite forces. I got Luke, Sophia, Sloan, Tristan. Table tennis ball launcher is fired. Compared to the impulse on the ball, the impulse on the launcher would also be the same. Right, so you guys know impulse is a transfer of momentum, right? Transfer of momentum is impulse. And you have two perspectives on that. Here, I should write this down, the equation for this. Okay. So you guys know impulse is a transfer of momentum, so like delta P, change in momentum. Okay. Now that could be mass times change in velocity, right? If there's some object, some mass, it's going to change its velocity, right? Simple, right? But where does that come from? That comes from applying a what for some what? An average force for some time interval. Yeah, force times time, right? If you saw a graph that was force versus time on the axes, then it would be the area under that curve. right? It's force times time, right? And so, no, the last question, you guys say, well, it's equal and opposite forces. Say if we got a launcher and a ball inside the launcher, right? There's some explosion here, pow, right? Pushes the ball to the right, pushes the launcher back towards the left. Equal and opposite forces. This force and this force are the same force, right? And those forces act for the same time interval. Maybe it's like a tenth of a second, right? Same force, same time, right? That's going to result in mass times velocity being the same value, just opposite directions for the ball and the launcher, right? Okay. Do you guys remember that magic school bus split? Pitcher throws the ball on a frictionless field. The ball goes one way. The pitcher slides back towards second base on a frictionless field, right? They both have the same mass times speed. Just one was towards the right, one was towards the left. So if you know both masses, you know the velocity of the baseball, you could calculate the velocity of the pitcher. Right? That was the first momentum puzzle that we actually solved in class. Was the magic school bus question. Right? It's that one right there. The same. All right. Momentum of an object is defined as the object's mass times velocity. P equals mv. Momentum is mass times velocity. Okay. Hey, how about this? Suppose there's two balls thrown at each other, and one has 1 kilogram times 10 meters per second to the right, and the other one has 1 kilogram times 10 meters per second to the left. And maybe they're on a collision course. What's the total momentum in that system? What's 1 times 10? Be 10. And what's 1 times negative 10? Negative 10. Put it all together. How much momentum? 0. It'd be 0 momentum in that system. You guys get that? Okay. What if I asked a different question? What's the kinetic energy? Would there be a bunch of kinetic energy? You could add up all the 1/2 mv squareds, right? Now that would be a scalar. But momentum is a vector. So it could zero out. Yeah, possible. Yeah. All right. Velocity of a moving object doubles. What else also doubles? All right, got momentum, right? Because that's mass times velocity. All right, whereas what about uh what does happen to kinetic energy? If you double the speed, kinetic energy increases by a factor of what? 4. Yeah, because it'd be 2 squared, because 1/2 mv squared, right? A factor of 2 squared. Right. And last class, somebody asked, well, what about this acceleration? Acceleration is just the rate change of velocity. So that could kind of be anything, right? Like if you hit a ball with a bat, that's a huge acceleration, maybe like 100 meters per second squared, just bam, right? But if you're in a car and you're speeding up slowly, like maybe like be like 2 meters per second squared, you could have the same change of momentum just over different time intervals. Yeah. All right. Yeah, Luke, Sophia, Sloan, Tristan. Cannon recoils from launching a cannonball. The speed of the cannon's recoil is small because yeah, cannon has more mass than the cannonball, right? So they get the same impulse, which is the same mass times velocity, right? But different masses going to result in different velocities, right? So the cannon is so massive, right? So that's from a momentum point of view. You could also think from a Newton's second law point of view, F equals ma, right? The large mass is going to not accelerate as much, right, during that explosion. Yeah. Now all right, so the red one, now the forces are the same, right? It's equal and opposite forces. And the yellow one, the impulses are also the same magnitude, equal and opposite. Right? All right. Piece of putty moving with 5 units of momentum strikes and sticks to a heavy bowling ball that was initially at rest. After the putty sticks to the ball, both are set into motion with a combined momentum of 5 units. That would be conservation of momentum, right? So we're looking at an inelastic collision. Right, momentum is conserved. So if there was 5 units of momentum in the system, then after the collision, well, they both roll off with those 5 units of momentum. Momentum is conserved. Yeah, I got Luke, Sophia, Sloan, Tristan. A table tennis ball moving at with 5 units of momentum strikes and bounces off a heavy bowling ball initially at rest. And sends the bowling ball into motion. The bowling ball is set into motion with a momentum of more than 5 units. So if that bouncy ball came in with 5 units of momentum, so 5 kilogram meter per second, see it bounces. Suppose it bounces off with 3 units of momentum the opposite direction. Right, guys, what is 5 to the right, 3 to the left? What's the difference? And don't say 2. What's 5 minus -3? 8. 8. Right? Here, I'll put that on. Let me draw that up. Draw that up. So you got, here's your bowling ball. Here's your bouncy ball coming in with 5 units of momentum. Go boing, something like this. If it had 5 kilogram meter per second here and 3 kilogram meter per second, but it changed direction, right? That's 5 minus -3 is equal to 8. Okay, that's the impulse, delta P, change in momentum. Okay, what does that look like on a number line? Here's 0, here's -3, here's 5. Okay, this difference right here is 8 units. Okay. Right. Ooh, guys, what's the maximum impulse that could have been delivered to the bowling ball? Like, I know it can be more than 5, but it can go up to what number? Go a little higher than that. Up to 10. Up to 10. It can asymptotically approach 10. And that would be if the bowling ball is much heavier than the bouncy ball and it's perfectly elastic. Right? If you put that all together, the maximum impulse could go up to 10, right? If the bouncy ball bounces off elastically. Right? All right. Got Luke, Sophia, Sloan, Tristan. 2 kilogram ball, 3 meter per second. What's the momentum? Six kilogram meter per second. Right. So mass times velocity. That mass, that velocity, put together. Yeah. 2 times 3 is 6. All right. Luke, Sophia, Sloan, Tristan. Collision is elastic. Yeah, those would all be conditions. Right. So I mostly focus on this gold one. Kinetic energy is conserved. Right. That's like the main marker. But that does go hand in hand with these other conditions also. Right. So like no lasting deformation. Last class they were asking some of these, so just to head these questions off. Let's do a counter example. Suppose you have 2 balls of clay and you throw them at each other and they stick together. Don't they also deform while they're sticking together, those balls of clay, right? Which would be inelastic. That's the opposite of this, right? That would be inelastic, right? But what I'm trying to get at is, doesn't a lot of the initial kinetic energy go into deforming those objects, right? That's where a lot of the energy is diverted. So it's some kind of force times distance. That also reminds me of, do you guys remember that ballistic pendulum? You fire a bullet into a block of wood and it swings up some height, right? Now, part of that, you had to use momentum. You cannot just straight use conservation of energy. You have to also go through a momentum for the collision, because when that bullet collides with that block of wood, it pushes away a bunch of those wood fibers. That diverts a bunch of energy that way. That would also be an example of lasting deformation, right? So, okay, going back to elastic. Ooh, I got Newton's cradle right here. You guys remember Newton's cradle? That's pretty dang close to perfectly elastic. Probably close, right? And those balls are definitely not deforming. Right? Yeah, and then don't stick together, because if they did stick together, that would be inelastic. Right? All right. So all those would be markers. All right, there we go. Got Luke, Sophia, Sloan, Tristan. Ooh, 7 in a row. Force of an apple hitting the ground depends upon. Yeah, all the above, all of those. So let's go here. I'll draw this out. See this one by one. Okay. So we got ground down here. Okay. Got a tree. Okay. And this apple is gonna fall. Okay. So this apple falls, okay. And then right here, it's about to collide with the ground. Oh, well, apple leaf right there. Okay. And then what? Right. Well, the force of collision depends on well, all those things, right? Because it was in all of the above. Okay. Let's get an equation going. So I know force times time interval. Uh, this is really an average force times time interval. That's like impulse results in mass times change in velocity. Okay. Now the question was about the force. So if you solve for that this average force, wouldn't that be mass times change in velocity divided by the time interval of t? Which, ooh, looks a lot like Newton's second law of motion. Does this pretty much say F equals ma? F equals ma? Right? Yeah, it sure does, right? Okay. So let's think different things can be going on with this apple. This apple has some mass m. Right. Now it has some speed crash landing, so some velocity maybe. Right. Oh, what if it just sticks in the mud? Like it goes from whatever this velocity is to 0. That could be a change of velocity. Okay. But what if it bounces? But boing, wouldn't it? Wouldn't the change of velocity be even greater? Right. Kind of like that bouncy ball bouncing off the bowling ball. Right. So if it comes up with 10 meters per second and then sticks to the ground, that'd be a change in velocity of 10 meters per second. But suppose it rebounds with 5 meters per second. Guys, what's the difference between 10 down and 5 up? 15, right? Because 5 minus negative 10 could be 15, like that, right? That's that delta V, right? Oh, right. So the faster it's falling, the more force. If it bounces, guys, if it bounces, is that more force or less force than if it sticks? That'd be more force. Yeah, because it'd be greater change of velocity. There'd be more force. Okay. And how about that time interval? So suppose that the ground was muddy, and so the time interval is like a whole second. It takes a whole second to come to stop. Right. So that'd be some amount of force. But what if it's a hard concrete ground? Right? And the time interval is like a hundredth of a second. Guys, if that time interval is getting smaller, 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 what's happening to the force? It's getting bigger, right? Because I see an inverse relationship. The smaller the time interval, the more the force. The larger the time interval, the smaller the force. Ooh, guess that too? Yeah. Okay. And that time, it's probably like a fraction of a second, just bringing the apple to stopping that collision. All right. I'm going in there. I got Luke, Sophia, Sloan, Tristan. Two gliders, same mass, same speed, move toward each other on an air track and stick together. What's the post-collision speed? Post-collision velocity. Oh, yeah, it would be 0 meters per second. See that real fast. Looks like this. That's it. That's the whole thing right there. That is it. All right. Yeah, 10:05. Yeah, 10:05. Got 5 minutes. Which has greater linear speed? Horse near the outside rail or inside rail of a merry-go-round? Here's your turntable, merry-go-round. Here's your horses. Which one has the greatest linear speed? So if you stood off on the side and you point a radar gun, yeah, one near the outside is moving faster, right? In fact, isn't its linear speed just proportional to its location from the center? So right at the center, it would have how much linear speed? 0. It doesn't matter how fast it's spinning, it has 0 linear speed. Point a radar gun says 0 meters per second. The further out you are, the faster you're going. If you're twice as far out, you're moving twice as fast. Linear speed. Okay, which has greater angular speed, as in radians per second? Horse near the inside or horse near the outside? Outside or inside? Angular speed. Same angular speed. Everybody has the same radians per second, same turns per time, right? Kind of like, don't they all make one revolution on the same time interval, right? Right. How about no matter what your latitude is on Earth, you make one rotation in 24 hours, right? Angular speed, right? All right. Sophia got that one. Whirl a tin can, end of a string. The string suddenly breaks, or you let go of string. The can will, the colors match. Which color? Colors match. Yeah, fly off tangent to a circular path. Hey, does this look like yesterday? If you turn gravity off, the planet will fly off tangent to a circular path. That's the same. Which law of motion is that? Newton. Yeah, Newton's first law. Yeah, Newton's first law of motion, law of inertia. Oh yeah. Got Luke, Sloan, Sophia, Tristan. Centrifugal forces, in quotation marks, are an apparent reality to observers in a reference frame that is rotating. Rotate. You have to be in the rotating frame of reference to perceive a force that feels like it's throwing you towards the outside. But if you're standing outside the system looking in, you say, well, there is no force throwing you out. There's inertia, makes you want to move in a straight line. And there might be some force acting as a centripetal force holding you in the curved path. Right? Right. So different frames of reference, different perceptions as to what the physics is. As the rotational speed of a space habitat increases, the apparent weight of the people inside also increases. Guys, if that O'Neill cylinder is not spinning at all, everyone's just floating around, that'd be weightless. If you give it a spin, then you feel like you have some weight. Now, it's not true gravity, but right. And then the faster you spin it, the heavier you feel. Yeah, right. O'Neill cylinder. All right, for the win. A car travels in a circle with constant speed. The net force on the car is directed towards the center of the curve. Guys, isn't centripetal force always directed toward the center? It might be a friction force. It might be some component of a normal force. It might be a string tension. But there's some force that's pulling you towards the center, keeping you in a circular path, right? Right. So it's centripetal. All right, to the podium. Ooh, got a special Christmas podium. All right, so Ollie and Luke runners up. Sloan with the bronze, Sophia with the silver, and the gold, Tristan. All right, nice job. All right, we got 30 seconds of class.